Well, hello everyone, and welcome to today's webinar entitled Assessing Soil Health, Measures of Soil Water Cycling. I'm Chris Boomsma, Director of Education at the American Society of Agronomy and Soil Science Society of America, and it is my privilege to be today's moderator. Okay, so with that, let's get started and go through a few items before we jump into today's presentation. First of all, I want to thank two organizations in particular. The first being our sponsor, the Walton Family Foundation. With their generous support, this webinar comes to you free of charge, which is fantastic, obviously, because some of you are getting a CEU without actually having to pay a fee for it. So it's great. And we are bringing some fantastic content to you in the soil health space. So again, great science brought to you by the Walton Family Foundation, and we appreciate that greatly. Secondly, we are partnering on this webinar with the Soil Health Institute. You're going to hear a lot more about the Soil Health Institute here shortly from our speaker, but we greatly appreciate them partnering with the Soil Science Society of America to dig into a really important, growing, popular topic in the soil science space, and that is soil health. So we want to thank everyone for being here today and for really coming and showing a lot of support for this topic. All right, moving on to the next thing, and that is some key notes before we get started. Inevitably, some of you may have some issues. Whatever that may be, I request that you reach out to Michelle Lovejoy, my colleague. You can see her email address, phone number on your screen at this time. Maybe it's something with your sound or something else with GoToWebinar. Please reach out to her first because I'll be monitoring the question box, all right? And so it's hard for me as your moderator to answer your technical questions. So reach out to Michelle, she'll get these things rectified as quickly as possible. Next, please note that this webinar is worth one CEU, Continuing Education Unit credit. It is either in soil and water management or professional meetings, and that depends upon your certification. But again, one CEU for this one. Next, please note that we will have a robust question and answer period at the end of the webinar for about 10 minutes. You can submit your questions to me at any time using the questions feature built into GoToWebinar. It's in the panel. Submit them to me. I'll take a look at them, order them, set them up, and then pose them to our presenter verbally during the question and answer period. So again, submit them anytime. We're ready for those. Next, note that this training session is being recorded. Both the recording and the slides will be available to you about 1 week after completion. Often though, that is sooner. All right, so we're going to get those to you. You'll be notified when they're available. Lastly, be on the lookout, please, for future webinars offered by the American Society of Agronomy and Soil Science Society of America in the coming months. We're going to really ramp it up come fall and winter. Now, that being said, I want to highlight a particular set of webinars that is coming up. Today's webinar is number one in a series that is being supported by the Walton Family Foundation and is in partnership with the Soil Health Institute. You can see the title of the webinars and the dates of these webinars. Now, there might be some minor changes here, okay? You know, things change with time if something comes up, but this is pretty much what we're looking forward to as we go into summer, fall, and winter. Be on the lookout for these. You'll see advertisements for them. You'll get emails about them. Please sign up. They are going to be free of charge, and I think you're going to like this series a whole lot. And the key is to be present for the whole series so that you get that totality of education. Okay, with that, let me introduce today's speaker. Today's speaker is Dr. Christine Morgan, who serves as the Chief Scientific Officer at the Soil Health Institute. Dr. Morgan is a former professor in soil science with the Soil and Crop Sciences Department at Texas A&M University. Her research emphasis, both in the past and now, includes assessing soil health, soil hydrology, pedometrics, and global soil security. So a lot of interesting areas of work for Christine. She's taught many introductory and advanced soil classes at Texas A&M University and with the Texas Master Naturalist Program. So she's a great teacher, and we're happy to have her teach you today. She's also a former board member of the Soil Science Society of America. We really appreciate her participation there. Lastly, she earned her master's and PhD degrees in soil science from the University of Wisconsin-Madison and her bachelor's in plant environmental soil sciences from Texas A&M University. So with that, I am going to hand it over to Christine. Christine, thank you so much for being with us today. And you are now going to be made the presenter. And when you're ready, you just go right ahead, show your slides. We look very much to your presentation. Thanks, Christine.
Okay. Well, I am excited to be here today and thank you for joining. And it really is an exciting opportunity to get to share with all of you the learnings that we are creating at the Soil Health Institute that we hope will advance adoption of soil health management practices. Today is the first part of the series, as Chris so nicely introduced. And today we're going to talk about measures of soil water cycling. And it's really exciting for me to get to talk about this because I've spent many hours since those days at University of Wisconsin-Madison. I spent many hours in the field doing all sorts of different soil physical measurements. I was trained as a soil physicist, as well as my many graduate students at Texas A&M University also have a lot of experience. And then on top of that, we've had this opportunity at the Soil Health Institute to measure soil health indicators of soils across North America. That's Mexico, the continuous United States, and Canada. And through that, I've learned a whole lot more about what's easy to do, what's not easy to do, and what's actually a measurement that's responsive to changes in management. So that's really picking up what's happening with those management changes. And I want to share all of that with you today. Before I get started, I do want to acknowledge many, many co-authors. At the Soil Health Institute, we have 16 PhD scientists. We're a nonprofit, but our goal is to get farmers and ranchers to adopt soil health management practices because of the economic, environmental, and social benefits of soil health management practices. But we are very science-based, and ultimately, as you will figure out from this presentation, I'm absolutely passionate about soil and about recognizing and measuring and talking about our soils as the natural resource it is and the importance that it has to both the United States and to the world. But first of all, a special thank you out to our team that have all contributed to this presentation today. Shannon Capolazzi, Dan Lipson, Michael Cope, Liz Reiki, Kelsey Grube, Mac Bean, Paul Tracy, Diana Bagnall, and our intern last year, Geneva Williams, who did a lot of downloading of weather data so that we could analyze all of this data that we're collecting. So thank you to you all you co-authors, and all the support at the Soil Health Institute. So why am I so passionate about soil and soil health? I think soil is a key component to many of our global existential problems that we have today. Improving our soil health has the opportunity to improve human health, food security, water security, energy security, improve our biodiversity, and also help our farmers and ranchers adapt and mitigate climate change. And so, in my 16 years as a soil scientist, every day I read the news and I hear about opportunities and problems that we face as a society. And I'm so excited to be a soil scientist and have the opportunity to contribute. And I know many of you on the line today are crop consultants, agronomists, soil scientists. Many of you, most of you are probably working in agriculture, and you as well have a lot to be proud of and excited about having the opportunity to work with our farmers and ranchers and manage this amazing natural resource that we have. But I will start today with a definition of soil health, just so we're all on the same page and we know what we're talking about. When I'm talking about soil health and measuring soil health, I'm talking about soil's ability, the capacity of soil to function as a vital living ecosystem that sustains plants, animals, and humans. And clearly, soil's function in water cycling is a big component of soil health. And a lot of times I like to start off with this picture. This is a picture that was provided to me by our CEO, Wayne Honeycutt, and it's a rangeland site in South Dakota. And it's beautiful because here's this nice fence line in the middle. On the right-hand side, there's a different management. Even though both of the sides of this fence are grazed, they're under different management. And you can tell that because there's different vegetative cover. If we actually dig down and look at the soil profiles, we can see the right-hand side of that fence has very different soil properties than that of the left-hand side of the fence, particularly in the topsoil. On the right-hand side, the soil is dark, likely from organic matter. The structure is very friable looking. It's what we call granular structure. And on the left, the structure is more coarse. It's more subangular blocky. It's lighter in color. And we can see that the management, even though these are the same soils, the management of these soils has affected their properties. And likely it's affected their nutrient cycling, water cycling, carbon cycling. And of course, what drives all of that is the soil microbiome. So I think this is just a really great example about how we as humans and our management decisions do affect the soil and affect it quite, visibly as we see here, but also biophysically and how it functions and participates in our world. Here are some specific examples about healthy soils cycling water. On the left-hand side, we have a field that's under no-till. And particularly we know this because of all the corn residue that's on top of the soil. On the right-hand side, the residue has been tilled in. And now we've had a crop planted, it's emerging, and there's been a rainfall. And we know there's been a rainfall because on the right-hand side, this is a site we've all seen as agronomists and soil scientists and crop scientists, where you get a good rain, you have this beautiful silt loam soil, probably, and you get a rain and the rain pulverizes that top millimeter or two of soil and you get the sheen. So now when the soil dries, it will crust over. So that's the future of this soil. But what we're actually seeing a picture of is the water's kind of puddling on the top of the soil. It's going to affect growth down here in this closed depression. And in general, it's also going to affect our trafficability. The left-hand side, you can imagine if you needed to, you could get out on this field much sooner than the soil on the right-hand side. Also, just in general, when it rains again, the soil is going to get splashed up onto the crop and perhaps share pathogens from the soil. And just in general, we really like the visual effect of the left-hand side, that this soil is draining, it's not crusting on the surface, and in general, it's cycling water much more effectively, which is going to lend to profit for the farm overall, and especially in the long term. Healthy soils also cycle nutrients. This is just another picture here. Again, we have this residue that's on top of the soil, and underneath you can see the soil is dark and very tilthy. And again, even though, in this situation, the soil is cycling water effectively, and because it's cycling water effectively, the roots are getting into the ground. They're not bothered as much during droughty periods, and they're able to get nutrients. Healthy plants and healthy roots can take up nutrients. Stressed plants and water deficient roots in water deficient soil can't pick up nutrients. So here we have the surface that's cycling the nutrients, and it's just all a positive feedback mechanism that we get better nutrient cycling when our soils are cycling water appropriately for the crop. And this is an example of what we don't want to see. This is another problem. In this situation, it looks like there was a planting, so we're in early spring. Obviously, there was a heavy rainfall, and now we have rills and gullies in the field. We have our topsoil with that high organic matter washing away, and this creates a lot of problems that are also costly to the farmer. We're losing our natural resource and the organic matter associated with it. We're very likely putting soil probably on the road that this picture was taken from, and perhaps that's going to cost the farmer. He's got to go and push the soil off the road. We have to clean out waterways when our soil erodes. And then also, we just have this field now with gullies in it, and we're going to reduce profits because the yield is not going to be very good where those gullies are. And over time, what you see often is plowing through these gullies, and over time, the soil just loses its productivity. So we don't like that. We like soils that are managed such that they stay in place when it rains. And though I've recently moved to North Carolina, when I lived in Texas for the past 16 years, and at least in Texas, I can report that rainfalls are getting heavier and heavier. When I was a kid growing up in Texas, a 5-inch rainfall was so exciting. My brother and I would go out and just play in it because usually it was summer and it was hot. but it was just really exciting to see flooding happen. Now, the last year I was in Texas, I think we got 4 or 5 inch rainfall. So, by the last one, you're just like, oh, whatever. But it's so important when we get rainfalls like that, we can't expect the soil to absorb all of it, but we do want our soil to stay in place. And so healthy soils are keeping the soil in place. And more importantly, you can see in this picture that the water is coming off the field clean. So it's not transporting phosphorus, at least, or at least the phosphorus that's associated with the soil particulates. So that gets to, why do we want to manage for and measure soil water cycling? Well, first of all, we do treasure our soils and their ability to cycle water, and it means a lot to the on-farm profit. First of all, yield, 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 and yield. And underneath yield, there's all the other components that go back to yield. And so one of them, of course, is trafficability. We want to be able to get onto that farm, into that field, and plant or do whatever we need to do. We know that last spring, that was a horrible example of loss of trafficability into our soils because it just kept raining. Drought resilience, as we get more intense rainfalls, but they're spread further apart, the soil has a greater and greater role to play to help us get that crop in between those rainfalls in our dryland soils, our dryland cropping systems. Nutrient efficiency, as I said earlier, healthy plants, unstressed plants can pull up nutrients and keep the nutrient cycling as well, and less nutrients being lost that has been applied to the soil. Water use efficiency, that works for dry land and irrigation, but certainly in irrigation, it's a big question of water use efficiency because it costs dollars to irrigate. Erosion costs money too. It's more of a long-term cost. Sometimes it's a short-term when you have to clean out your ditches, but for sure it's a long-term cost because you're losing that productivity of your soil. And surface water quality, a lot of times we think about that as an off-farm profit, but for sure, if you're a rangeland person and you are capturing surface water, you certainly want it clean for your animals to also maintain their health. But on top of on-farm profit, we also have these off-farm benefits. Society benefits from farming and ranching in so many ways, and it's because of the ecosystem services of the soil. So some examples are, of course, surface water quality, nutrient efficiency, water use efficiency, and our fisheries. If we have clean waters and waters without nutrients, our other animals that we share the planet with also have healthy environments to live in. And lastly, I've listed ecosystem service markets. They're just now starting to form. And though a lot of the ecosystem service market talk is about soil carbon, and there's for sure more markets emerging around carbon, the Ecosystem Service Market Consortium program, ESMC, is stacking services. So they're interested in crediting farmers not only for carbon, but for water quality and water quantity. So if we can measure our soil water cycling improvements and potential, then there is also that potential for that ecosystem service market. You notice I didn't put a bullet on it because it can float right over there to the indicator of on-farm profit too. So in general, we treasure soil water cycling. And when you treasure something, you measure it because you want to know how it's changing and how your management is affecting it. And everybody knows this, but I'm a soil scientist, so I have to show beautiful pictures of soil structure and of course what you don't want your soil structure to look like. But when we're managing for soil health, a lot of our management decisions affect the soil structure. And that soil structure is the key component to our water cycling. So when we affect our structure, of course, it's a key driver of soil, water, plant, and nutrient relationships. And soil structure is a key physical indicator of soil hydrology and biological function because structure changes in the soil because of the biology. That includes the roots, the wetting and drying cycle, and of course, the microbes and the megafauna. By megafauna, I do mean worms. There are some big ones out there. So how are we going to measure something? If we treasure our ability of water to cycle or soil to cycle water, what are the measurements? And so I did a little brainstorming and thought, okay, what could we measure? Of course, we could measure bulk density or penetration resistance. You know, that kind of has some information about the porosity and how the soil structure is formed. Penetration resistance is a real direct measurement of what those roots see, right? Like how the roots can get into the soil. Infiltration, of course, is important. I showed examples of that. Another measure that's like infiltration is saturated hydraulic conductivity, and I'll go into more details about those. Of course, there's available water holding capacity, and when I mean available, I mean plant available water holding capacity. So what is the water being held in the soil that is plant available? Aggregate stability is a very popular soil health measurement, and it's really related to all of the above, especially infiltration, surface infiltration, and available water holding capacity. Aggregate stability, unlike the other three, it's not a direct measurement of a soil function, but we all know that it is a good indicator of the functions above. And then when we think about the practical side of what we're measuring, these are the considerations that I think are important. First of all, ease of measurement. And take that from someone who has spent daylight to dark hours in a cornfield in Wisconsin, measuring a lot of hydraulic conductivity measurements. We want it to be easy. We don't want things to be too difficult because they have to be reproducible. And for consulting scientists and consulting agronomists, we need it to be reproducible and doable by all, right? Transferability or quality of the measurement. This is something that I'm going to make a point of today. And what I mean by transferability is once we make this measurement, the question is, how useful is that measurement tomorrow? And if we make that measurement a year from now, 6 months from now, or in another field, how comparable are these measurements? So one example would be, is we all know that infiltration, water infiltrating on the surface of the soil, is really dependent on how dry the soil is when the water's added, right? Now, that's really not what we want to measure. We want to measure the soil's ability to conduct that water and capture that water, but we just have this problem with antecedent moisture that gets in the way. And that's what I mean by transferability. Does your measurement eliminate the antecedent moisture question so that we can make a measurement today, tomorrow, 10 years from now, and they're comparable to each other? And that also gets back to that value of our soil function versus the cost of the measurement, right? If something is transferable, it could have a greater value. If that measurement reflects a key management issue in the region, it has greater value. And so there's this constant balance between value and cost. And that gets to the last consideration that I will not talk much about today, because it's really, that's your consideration as a farmer, as a crop consultant, as an input advisor. You know your farmers' fields, you know your fields, and you have to decide what your key management issues are for your region and your cropping system. And certainly that needs to go into the calculus of a measurement. So I'm just going to go through these measurements. I'm going to talk about the pros and cons. I'm going to talk about what we know about their response to management change. Okay, so the first measurement that I mentioned is the penetrometer. It's definitely a relative measurement. And what I mean by that is that there's so many things that go into that penetration resistance. It's a very simple measurement. You push it into the ground. And this is one of our SHI scientists that's pushing it into the ground. And let's see, I think I'm on pointer. And if I get off of that, nope. I was looking to see if this is actually a video. Oh, there we go. So you can see Shannon, Dr. Capilazzi, is pushing this penetrometer into the ground. She's trying to be consistent with her force, but you can imagine, that someone that perhaps lifts weights every day and is maybe, 100 pounds heavier than Shannon might have a different concept of what the force is that you push the penetrometer in the ground. So the first point is that who takes the measurement matters. How resistive the soil is matters, and how consistent you are with that force. Because essentially all you're doing is you're pushing that penetrometer in the ground and you're just measuring how much the soil resists that push. So this is a really easy measurement to take. The nice thing is it's a depth measurement and it tells you what the root sees, so I wrote that it quantifies the root experience. But the problem is it's a function of compaction, which is what we want to measure, but it's also a function of the texture, the clay and the sand and the silt content, and it's a function of the water content. So there's just a lot of stuff. And then I should have put here, it's the function of who measures it, right? So what their concept is. So there's just a lot of things that go into this that make it really hard to analyze the data. Conceptually, it's very clean. So what I would say, if you want to use the penetrometer to show your soil water, soil rooting relations, it's best for comparison sites. So it's that idea you have two fields and maybe half the field you break out and you do cover crops in. It's a good comparison to demonstrate to farmers, okay, you do penetration resistance with cover crops and those without the cover crops. You hope that they're the same moisture. They may not be because of the cover crops. And it's a comparison of what the root sees. And I think I'm going to leave penetrometer at that because there's just a lot of uncertainty with it. Bulk density, more transferable, great. It's a standard measurement. You have to collect soil out of a known volume. That's the problem. And the larger the volume, the better the measurement. So in this example, this is a 3-inch diameter soil core, and we pounded it into the ground, and now we cut the top off, and now we know the volume. We dry the soil, and we weigh it, and we have the mass divided by the volume, and that's our bulk density measurement. Pros and cons. Bulk density is difficult to do well. I say this as, I don't know how many graduate students I've advised, but it's really funny, being in soil physics, a lot of my grad students are out calibrating soil water measurement instruments. And, so I've looked at a lot of bulk density measurements, and you can tell the person that you send out, I classify them as, do they have low or high standard deviations when they measure bulk density? So clearly there's a carefulness factor that goes into measuring bulk density. It is repeatable and it is needed for soil carbon stock estimates, but probably if you're really just looking for water movement, it's probably not the measurement that you want to take. Here's an example of the data from our North American project to evaluate soil health measurements. So this is a project where we have looked at 124 long-term research sites. So these are kind of plot style research sites across North America. So that's Canada, the United States, and Mexico. They all have at least 8 years of some continuous management change, and usually there's a control of business as usual, and then some soil health management treatments. The beauty of this data set is all these sites were sampled 97% of the sites were sampled in the spring before planting in 2019. So we've just been able to start analyzing this data. So these log ratio graphs that I will be showing a lot today, I'm going to get you familiar with them now. Essentially, on the x-axis, what we have is some change value. In this example, it's change in bulk density, and it's a percent change. And you might say, a percent change from what? Well, numerically, the what is this zero line that I've highlighted that goes up and down. And in this example, since we're looking at tillage, the effect of tillage intensity, the percent change in bulk density from the intense tillage. So these are ratios. For example, this first line is minimum tillage, the ratio of bulk density from our minimum tillage plots versus our intense tillage plots. And you can see there were 72 that were the ratios that went into this mean and this 95% confidence interval. The next one is minimum tillage versus moderate tillage. So now the what is not our most intense. And now you can see the mean and the confidence interval. And the deal is if the confidence interval does not intersect this zero line, then that mean is significantly different from whatever ratio you're comparing it to. So in this example, we have minimum versus intense tillage, n equals 72, minimum versus moderate tillage, n equals 30, moderate versus intense, n equals 22. And then if you add them all up together, we're doing overall and it's really overall relative to, it's a combination of those three below. And so what if we just want to look at the overall, what we can see is that tillage alone tends to decrease bulk density by about 3%. That's good news. We like to hear that. Now, in the same data set, we had a lot of data on cover crops and a little bit of data on organic amendments, like, audio connection restored. So I'm assuming y'all can hear me. Okay, so won't kick my cord anymore. Be very careful. So essentially what we have here is that our cover cropping did not create a significant difference in bulk density, and our organic amendments did not create a significant difference in bulk density. So, a lot of the lack of significance was because our N was much lower, but also, nothing affects bulk density like tillage. So this is just an example of bulk density in our NAPESHM project. And from here on out, as I talk about a measurement, we'll have these kinds of comparisons. Okay, so we did bulk density and penetration resistance, and I would say that I've started out with the measurements I think I would prioritize the least. Next is measuring infiltration. And, if you go back and remember that picture that I showed you of, the no tillage versus conventional tillage and the difference in how the water was standing on top of the conventional tillage and the soil looked different, that's something that we really want to capture. And one way that we do that is I pulled two methods that I thought were standard and that everybody could access. And they have different properties to them. But the first method, I call it the NRCS infiltration method. I'm sure it's not the NRCS infiltration method per se, with what it's called, but you can get the method at an NRCS website, and it is one that they use for a lot of their soil quality measurements. And it's a gorgeous measurement because it is so easy and it really requires very little equipment. So first of all, the pros of this measurement is that it is cheap and easy. Now, how do you do it? You put a 6-inch diameter ring into the ground, you put some plastic on, you put water into the ring until it's 1 inch high, into the ring, and then you remove the plastic and you time the amount of time it takes for that water to infiltrate, okay? And then you repeat it after the first inch has infiltrated, you repeat it, and that second time kind of gives you, the first time gives you some information on the infiltration at whatever the current water content is. So if it's dry or moist or whatever. And the second one kind of gives you more information about, maybe removes a bit of the effect of antecedent moisture, but not a whole lot because it's not a big volume of water that's going through that soil. So the pros of this method, it's very cheap and it's very easy to understand. And NRCS has a lovely PDF where you can get all the instructions. They're very clear. Also, there's a lot of literature that uses this. I'll show an example of that. You can take more than these at one time. You can put a bunch out. You just have to keep your eye on them. So I say the cons are is it requires attention. But again, this comparison, it's best for comparison of sites at the same time. So once again, it's a really good method to use if you're just comparing, if you have, again, that split field scenario and you're working with farmers on trying some different management practices. The step up from that is the idea of getting the saturated hydraulic conductivity, or what we call KSAT. And what happens with KSAT, as you can imagine, is that we're saturating the soil and now moving water through it. So now we're not dealing with the antecedent moisture theoretically. Of course, a lot of my work is on vertisols, and you can imagine, when a soil is cracked, you're not, that's just a different case whatsoever. So essentially, this instrument that I'm showing you here costs about $3,600. So that's probably a con that it's expensive. But the nice thing is that it is repeatable and it's automated. So you can set this instrument up in a few minutes and then go off and do something else. And the instrument uses the dual head calculation method, so it will infiltrate water at 2 different pressures, and it uses some equations to get hydraulic conductivity from that. And if you're interested in that and all the equations, you can certainly look it up. This is a Saturo device, S-A-T-U-R-O, and it's sold by Meter Group. And I've used a lot of, I've used the Guelph, I've used some crazy hood infiltrometers, which were fun but complicated. I've used amusimeters. I've used my own falling head and constant head with Marriott bottles. I've used a lot of different surface infiltration measurements, and I like this one because it's easy, but it does have, a capital cost to it. The cool thing when you measure your KSAT is that it quantifies that soil function, and it is repeatable, and it's comparable and it's transferable. And this might have value if your farmer or rancher is interested in marketing an ecosystem service that has to do with water capture. So here are some examples. This is an example of using that NRCS method. It is by my former colleague, Paul DeLon at Texas A&M AgriLife Research in Vernon, Texas. And he has some long-term trials where he is looking at conventional versus no-till and the effect of cover crops in the area of the rolling plains of Texas. So it is dry and it is hot, and I suspect today it is very hot. And Paul's dealing with sandy soils that crust a lot, and he's trying to, but also worried about the cover crops and pulling out water. And so he's really looking at the water relationships associated with soil health management practices. And in what he's found is that this method is pretty good, that it's showing differences. Here's some plots he has in Haskell that's showing that the no-till has a higher infiltration than the conventional till, and some plots he has in Chillicothe that's showing he's got conventional, strip, no-till, and no-till cover crops. And so in Chillicothe, he's really in his data that he has found out that the cover crops really make a difference for his infiltration. I do know that Paul has published some of this data, but I neglected to get the publication from Paul. I think he published it in Agronomy Journal and within the last couple of years. So if you're interested in his work, you can Google DeLon and Google Scholar and find his work. Back to the NAPSHM project, we have done some similar work. And so again, the example that I show you here is tillage intensity, and we're looking at the saturated hydraulic conductivity test. So again, we were able to use this test across North America all in the same couple of months because we're not worried about the effect of antecedent moisture. If you'll remember in Paul's work, I can't go back, that's weird. In Paul's work, those were plot comparisons. So he was taking the measurement at the same time. So in this example, we're in the same y-axis as before. We're looking at tillage intensity. Most interesting probably is this overall 118 experimental units are compared. Percent change is on the x-axis, and here is that zero line. And remember, we don't want anything intersecting that zero line. In the 95% confidence interval, that's a p-value of 0.05. So really, only if we compare minimum versus intense do we see a change in saturated hydraulic conductivity. This is a con of saturated hydraulic conductivity. It is a log normal distributed property in any field of any soil. And I'm sure most of you all know this because you have seen that you can get a really high hydraulic conductivity and then move over 6 inches and then get a really low hydraulic conductivity. And so the variance is really high in this kind of measurement. And that's why we're not seeing some significant differences. I haven't had the SHIPS team do this yet, but I suspect that if we went to a 10% confidence interval, we might start seeing some significant differences. But at the end of the day, it's not about statistics and significant differences if you're working with your farmer on adopting soil health management practices. It's about, does an extra 2.5 inches of infiltration of a rainfall in an hour, is it useful for your farmer? And though any one measurement may not be significant, when you add it up over the course of a growing season of how much more water is captured rather than runs off, that number can have a lot more significance. Okay, it's working now. Okay, good. That worried me. My slides were not advancing. Okay, so that was infiltration. Next, we have available water holding capacity. And essentially, water holding capacity can be measured many different ways. We're looking at the amount of water that's held that's available to the plant, so field capacity minus permanent wilting point. And we can measure it with an intact core, which I described earlier for bulk density. The NRCS method is an intact clod. So always know when you look up in soil survey to the available water holding capacity, that value was created by looking at the volumes of clods. And then some soil health labs will do repacked soil for field capacity. And what I have today is a comparison of intact versus repacked. I'm sure you can imagine what that's going to do, because my point here is that it's all about those pores. When you change your management, it's about the macropores that affect available water holding capacity. I don't know why my slides are not advancing. Oh, okay. So here's available water holding capacity of intact versus repacked soils. Once again, this is tillage intensity, and I just want you to see this gold line that when we do available water holding capacity of intact soils, they're significantly different. They're responding to tillage. When we do it for repacked soil, not so much. So if you do this measurement, we definitely encourage you to do it in soils in their intact environment. So what overall does water holding capacity do when you change soil health management? So here we have a picture of tillage versus no-till, and I think this is just a fun picture because it just kind of gives you an idea that, you know, more water is held, it's available for the plant in no-till. But the numbers are over here in the bottom right-hand corner, and we did this analysis for tillage, cover crops, and adding organic amendments. Again, the organic amendments were not significant. They did trend in the right way, but they were not significant. And so, and our N was really small. So I wouldn't put a whole lot of concern into that not being significant. But essentially, tillage and cover crops have equal influence or almost equal influence on the ability of what to increase that available water holding capacity of our soil. And in general, no-till can add about 2,200 gallons per acre of water to your soil. But the cool thing now about available water holding capacity is we don't have to measure it. We actually, through this NaPSHM project, have developed what we call a pedo transfer function. And that's at the right-hand side of this graph. And we know that available water holding capacity, and this has been in the literature for a long time, it's a function of soil texture, so clay plus sand, and it's also a function of increasing organic matter. But up until now, we didn't have a good data set to create those functions. And these functions that I'm showing here are just an illustration of the outcomes of our new pedo transfer function created with our NaPSHM data. And it was doable because we had on-site comparisons of business as usual and management increasing the organic carbon. And when management increases your organic carbon, it also increases that available water holding capacity. So this is just an illustration. On the x-axis, we've put clay content. On the y-axis, we've put available water holding capacity. And essentially, we can see as we increase organic carbon, we are increasing organic or available water holding capacity. So we don't have to measure it. We can model it. And this pedo transfer function currently is available in Comet Farm. We haven't released this module in Comet Farm, but we're hoping to soon. So essentially in Comet Farm, you can go to your field location and put in your past management. You can create future management portfolios. Of course, the Comet Farm uses DACENT, so it can tell you how your organic carbon will change with management. And then that increase in organic carbon will pop over to this pedo transfer function and then deliver to you information on how your available water holding capacity will change with management. So our last measurement that we have is aggregate stability. And I'm not going to belabor the fact that aggregate stability is also very important. Again, it's not a direct measure of soil function, but it affects infiltration, water holding capacity, aeration, and resistivity to erosion. And it's very responsive to manageable factors. And there's a lot of different ways to measure aggregate stability depending on what lab you send it to. It really affects, what measurement is going to be made. So just really quick, we have the Cornell sprinkle infiltrometer, where you put aggregates in, you sprinkle water, you look at how many are stable. We have a wet sieve method. This is the old tried and true Kemper-Rosenau method, where you put your aggregates into a shaker and then you change to different water, and you just change to a dispersing solution and you look at your aggregate stability. This is a new method called Slakes. It's a smartphone app. I really like it. You can get it right now on your iPhone or your Android. You could download it while I speak. It's called Slakes, S-L-A-K-E-S. And you just put some PEDs into a Petri dish, you add water, and then it films how your PEDs disperse over 10 minutes. And it just looks at that initial area over the dispersion area and gives you a stability index. And then there's another soil stability index. It's created by Alan Franzenlubers. He's published a lot on it because he's really looking at those mechanisms of carbon storage. And essentially he does dry sieving and wet sieving and comes up with this mean weight diameter of aggregates. So the important thing to notice right here is the cost. These all have different costs. They're all about $20 a sample, except for Slakes, because you can do it yourself. I put $2 a sample because I was estimating what it would take a lab to run Slakes. But anyway, the important thing to know is all these aggregate stabilities are different measures of aggregate stability. All the methods are different measures. They are not really well correlated. However, they have the same trends. So each of these figures is a different measure of aggregate stability. And the box plots are colors, and the colors are the same. So we have row cropping, integrated row crop, perennial, and woody perennial kind of managements. And what you can see is they all trend the same way, right? The more perennial your system, the greater your aggregate stability. But they're not correlated to each other very well. Some of them are correlated to organic carbon, and like Slakes is not. So I just picked Slakes because they all behave this way. And essentially, aggregate stability is responsive to tillage, it's responsive to cover cropping, it's responsive to residue management, and it's responsive. This is a more continuous measurement where we have living roots on the x-axis and aggregate stability on the y-axis. And as your living roots in the soil increase, your aggregate stability increases. So what we have here with aggregate stability, here's the Cornell sprinkle infiltrometer. And what we're seeing here are those ratios, percent improvement with a soil health management system. And you can see almost all of these aggregate stability measurements responded to decreased tillage intensity. Two of them, wet sieving and the wet soil stability index, responded to adding organic amendments, statistically significant at a 0.05 p-value. Implementing cover crops, we had Cornell and Slakes responsive. Removing crop residue, Cornell and Slakes was responsive, and none of them really responded to crop rotation. So ultimately, Cornell sprinkle infiltrometer was kind of the most responsive to management, as well as Slakes. So what does that mean for conclusion of how do we measure water cycling in soil? So I've kind of showed you the proof of why I have drawn this conclusion that I share with you today. If I could only make one measurement and I had very little money, I would measure aggregate stability and I would download it on my smartphone. Aggregate stability captures many changes in soil health. You can download and use this app today. There are more improvements coming this fall. Because of this project, we identified some problems with it, and so we're going to make it a little more user-friendly, and that should come out in a couple of months. There are no lab fees. I hope that some labs start using Slakes so that we could get a good national database on it. And it's not a direct measurement of any particular soil function. Available water holding capacity, super important to our farmers. We can model it, we don't have to measure it. But it is a function of organic carbon and soil texture. There will be a decision support tool available where we can use it to show benefits to our farmers. So this is another essentially free decision tool that you can sell as a crop consultant to work with your farmers in getting soil health changed, soil management changed. You can't sell the Comet Farm simulations, I'm sorry. You can sell your services to developing soil health of the farm. And the nice thing about available water holding capacity is it directly quantifies changes in soil function. Lastly, infiltration. I love it. I'm a soil physicist. I'm very partial to it, but I've ranked it down here at the bottom. If you're thinking about entering ecosystem market, or you want to do a big study that looks at effects of soil health management, KSAT is a really nice way to go. But it will have some costs. And $3,600 actually probably isn't a lot at the end of the day, but your time is also worth something. So you just need to decide if it's worth your time, if the information you use could be marketable. And then surface infiltration is that NRCS method is fantastic if you want to just do some side-by-side comparisons. And I think for measuring water cycling in soils, that's probably our best recommendation to date. If you want to learn more about these measurements, we'll go much more into depth of them at our Soil Health Institute annual meeting next week. It's virtual and it's free, but you do have to register, and you can find registration on our website. Lastly, all this data would not be possible without our partnering scientists that put their sites up for us to come out and measure, and we really appreciate all of their efforts and their cooperation. And the financial aid for all this huge project is the Samuel Roberts Noble Foundation, General Mills, and the Foundation for Food and Agriculture Research. So we want to thank you for your financial support and thank our partnering scientists for their generosity and cooperation. Lastly, definitely thank the Walton Family Foundation for their generosity in sponsoring this so that we could get this information out to you at no cost to you. And with that, you can contact me at cmorgan@thesoilhealthinstitute.org, or also just look on the website and you can find the email addresses of all of our leadership. And with that, Chris, I'll turn it over to you.
Fantastic. Thank you, Christine. All right, everyone, you just saw her email, and that's important because we got a lot of questions coming in, Christine.
Oh, no. Don't kill me.
No. We're going to make you work hard here to the very end.
Let's get through it.
A lot of them, though, are really specific and technical, which is good because I think we can probably move through them pretty quick. But everyone, if we don't get to your question, I'm sorry. Just reach out to Christine at the email address on your screen at this time. All right, with that, let's get started. First of all, Christine, can you please explain to the audience what you mean by antecedent moisture? What is that by definition?
Yeah, I kind of got a little jargony. Antecedent moisture is the moisture at which you start the measurement. So if it's a dry summer and you do the measurement in August, that antecedent moisture will probably be pretty low, maybe close to wilting point, where antecedent moisture maybe in the spring is closer to field capacity. So it's just whatever moisture content that you do the measurement at without altering the moisture content.
Okay, very good. Now going back to your the discussion you had around the penetrometer, can we measure soil crust with the type of penetrometer that you showed?
No.
Nope. Okay, bam, that's a quick answer. I like it.
There are laboratory methods, and a lot of like tillage labs can do that kind of stuff, but no.
Okay.
Use your push on it.
Any other comments on soil crusting and measuring it though?
Not,
and as an indicator of soil health, or
a lot of times we measure the roughness, and that's kind of a physical parameter we're very interested in. But yeah, I'll need to think about that.
Okay, that's fine. Absolutely. All right. Do you think we should correct penetrometer resistant data for water content and clay content if it's done by the same person, even in the same day? That is, if the measurement is done by the same person in the same day.
You could do it. It's complicated. There's a paper out where we have done it. It's in the European Journal of Soil Science, and I don't know what to do, but I can send the paper or something. Anyway, it's the European Journal of Soil Science. It's a 2020 paper, and it has my name on it if you're interested. And I would say, but we used hydraulics. We did not use a human being to push it down, but you could do it. It'd take a pretty big data set and some machine learning.
Okay. Well, folks, if you are interested in that paper, please reach out to Christine and she can probably get that to you, or just Google your way until you find it, I suppose.
Yeah,
So,
I think it's
all
open.
right. Oh, good. Open access would be perfect. Excellent. Okay. Next one, we're going to keep rolling. Would you remove residue before the infiltration measurement to get the soil infiltration rate, or would you keep the residue present so you can better represent the management system?
It would depend on how easy it was to put the ring into the ground. If the residue is going to make the ring kind of wobble as you push it into the ground, you don't want to do that. So like big corn stubble, definitely remove it. Really resistant wheat stubble, wheat, whatever, shafts, I would remove that. But if it's just a little stuff and you can pound it into the ground nicely and get that and not wobble it, if you know what I mean, like disturb things a lot, leave it there.
Okay. Very good. Thank you. Next, can you clarify the difference between water holding capacity and water retention?
Water retention is the water content at any given suction. And water holding capacity, I should be calling it plant available water holding capacity. And that's just defined as between field capacity suction and wilting point suction. So I probably need to be more careful with my use of words.
Okay. Well, you clarified, so that's good, right? That's all
Yeah.
right. All right. This person says, what organic amendments specifically were added or tested as part of your available water holding capacity?
Okay, now I can put a shout out for our societies. That paper is Norris, Norris et al., and it is in the Agronomy Journal, and it is open access, and it is available now. I think it was published in May, June,
Okay.
May,
Hmm.
and you can get it open. Google Norris, NAPESHM, and it'll come straight up. And,
Awesome.
and it describes the manure systems.
Okay, great. Well, there you go. It's pretty great that you can give us a reference right off the cuff like that. Well done. All right. And because actually it's a very important question because more than one person asked that. So,
Yes, so if y'all are interested in any of the methods or the sites in that NAPESHM project, it does not have results yet. We're going to submit results for publication this fall. But if you're interested in any of the methods or the sites, you can go to that Norris paper. It is open access and you can have at it. And it also has all of our partners and their citations and their papers on the work.
okay, very good. Okay, the next one is a person seeking some clarification on something that you posted, I believe, in a graph, but we can
Okay.
get clarity here. The slide that dealt with available water holding capacity stated that cover crops no-till increased water holding capacity by nearly 2/10 of an inch in the top 6 feet of soil. Was that supposed to be in the top 6 inches of soil? Just looking for
Yes,
clarification.
it was supposed to be the top 6 inches.
Okay, all right, there you go.
I'll change that slide before we post it.
That's all right, no problem. All right, there we go. Um, this person asks, when you talk about transferability, do you have to measure your indicator in the very same spot, site, or parcel year to year?
I would get close. You don't have to be right on top of it, but don't like if you're doing a hydraulic conductivity or something, don't measure it on the back slope one year and on the foot slope the other year. Just stay in the kind of same field, same landscape position, and you'll be all right.
Okay. All right, I think I got time for about one or two more questions, folks. So again, take down that email address on your screen at this time if your question is not getting answered. All right, next one. How does the addition of fertilizer, or what does the addition of fertilizer have? What impact on soil bulk density? And what impact does it have on water cycling?
Okay. Well, I would say that if your plant is healthy, it's going to put out a lot of roots and it's going to improve both bulk density, decrease it, and it's going to improve water cycling because the roots are big conduits of water. So I would say that, it depends, but essentially you want a healthy, uh, a, soil plant with healthy roots. So fertilize as needed.
Okay. And I'm going to end on a bigger picture question that one of our attendees submitted. To what extent have soil health measurements been officially accepted in the agriculture community?
Oh, that's a great question.
Yeah.
I think that in general, people are really interested in it, which is why we did this work. Like I didn't say it, but this work was really like what to measure and how to measure it was a huge effort by the whole soil science community. Many soil scientists, members of AASA and ASA came together and helped the Soil Institute develop the list. So first of all, in the ag industry, I think there's a lot of people wanting to know, like especially like food and beverage, they want to know what their footprint is on their agricultural, environmental agricultural footprint is. So everybody's clamoring for like, what do I measure? How do I measure it? And I think a lot of measurements are well accepted. For a farmer to accept a measurement, it's got to have a management decision based on it, right? For a food and beverage company to want a soil measurement, it has to have some relevance to some improvement of, environmental quality or carbon sequestration tied to it. So it depends on the stakeholder. It depends on what they want. But many of these soil health measurements, I think people are using them. I mean, not everybody knows what to do with it, but for sure
Mhm.
we're taking them.
All right. Well, thank you for offering perspective at the end. And I got to say, Christine, great presentation. I got many comments too, not just questions, saying that they appreciate your presentation, great slides, and they appreciated how you were right to the point with all the information you presented. Very clear. So well done. We thank you very much for being here today. I want to thank one last time our sponsor, the Walton Family Foundation. Just very generous support here that has brought this great presentation to you free of charge. So that's wonderful. And again, please be on the lookout for more presentations on soil health. This is only part one. There are more coming, so we really want you to join the rest of them. And with that, folks, we are out of time today. We do appreciate you joining. Tune back in for more of these webinars. Christine, thank you very much. Everyone, have a great day. Have a great week. Take care. Bye-bye.
Take care, everybody. Bye-bye.